In Lab 1.1, our purpose is to recognize, describe, construct, and extend geometric patterns. The manipulatives that we will use will be the pattern block pieces. If you will get out the blocks and separate them by colors and shapes, it will make it easier as we begin looking at different patterns. We're going to start with a very simple pattern. We'll be using the triangles. We'll start out with our first of the pattern to be the green triangle. Our second in the pattern will be two green triangles put together. Our third in the pattern will be three green triangles placed together. So imagine yourself as being an early elementary, first grade, second grade, and you're looking at what I'm doing. Could you ask the question now at this point, what will happen next? Do you think the students would be able to say, oh, there's going to be 4 green triangles in the fourth? We want to begin looking at our information in a table. We want to look at the position that each is in and the number of triangles that each has. So I would see that the first position has 1 triangle. The second position would have 2 triangles. The third position would have 3 triangles. And then after you have built enough, you would want to ask your students what will happen next. And how do you know that that is what would happen? And so they would then predict how many triangles there would be in the fourth, how many triangles there would be in the fifth, and they could actually build those. As the students begin to get older, you might ask them, okay, how many triangles would there be in the 10th? How many would be in the 20th? And in the middle school, you would want them to be able to make a generalization about no matter what number position I give you, what would be the number of triangles that you would have. And so now you're beginning to make a generalization about the situation. And so there would be n triangles for the nth position. And this now begins the generalization. All right. Let's look at a second pattern. We will let our first position be a triangle. And we will let our second position be a triangle and a parallelogram. Our third position is a triangle, a parallelogram, and a triangle. Now I'm trying to go slow enough so that you are doing this lab with me. In the fourth position, we would have a triangle, a parallelogram, a triangle, and a parallelogram. Need to scoot these over a little bit so that I can get all of them on there on the screen. So this now is my fourth. Now if I ask you what would happen on the fifth, that would be easy. But now when I ask you what would happen on the 10th, you might have to think about it. And then when we look for our generalization, we're going to have to think about not only the number of triangles, but we're going to have to think about the number of parallelograms. So let's make a table. We'll have our position. We will have the number of triangles, and we'll have the number of parallelograms. So in position 1, I would have one triangle and no parallelograms. In position 2, I have one triangle and one parallelogram. In position 3, I have two triangles and one parallelogram. In position 4, I would have two triangles and two parallelograms. So now without building the fifth, we can see a pattern that is happening with the triangles. So we can predict that the fifth and sixth might have three triangles, and for the fifth and sixth on the parallelograms, you might have two for the fifth, but for the sixth, you might have three. And then you can build that to make sure that that's what's happening. All right, now we want to skip and we want to see if there is some pattern that we see between the numbers of triangles and the position and the number of parallelograms and the position. So we're going to skip now and go to the 10th position without drawing it out or without representing it with our manipulatives. I want you to stop now and think how many triangles there would be and how many parallelograms. All right, now, do you see a pattern in how the numbers end? If it's an odd number, like the first position and the third position, the shape ends in a triangle. If it's an even, the shape ends in a parallelogram. So when I get to the 10th, it's even, so I know that I'm going to end with a parallelogram. So if I look at the pattern, the difference in the position is 1, 1, 2, 2, 3, for 7, it would be 3. For 8 and 9, it would be 4. And for 10, it would be 5. So there would be 5 triangles, and we know that it's going to end in a parallelogram. But let's look at the difference in the position and the number of parallelograms. So there's a difference of 1, 1, 2, 2, 3, 3. So there will be a difference of 4, 4, then 5, 5. Now we want to try to come up with a generalization about the shape. How can we calculate any number, any position that I ask? So I'm going to let you think about that a minute. I want you to look at the evens. And how the triangles are related to an even position. So we could say if the position is even, the number of triangles is half the position. So if the position is even, the number of triangles is half that. So 2 to 1, 4 to 2, 6 to 3, 10 to 5. So if I said, how many triangles are there in the 100th position, then you know that there would be 50. It would be half of 100. Or if I ask you the number of triangles in the 50th position, 50 is even. So you know there would be 25. So we have a generalization that occurs if we know an even position. Well, what if the position is odd? We look at the number of triangles. We have 1 to 1, 3 to 2, 5 to 3, 7 to 4, 9 to 5. We have 1, 2, 3, 4, 5. We're dealing with the counting numbers. So if I take the position, if the position is odd, if I add 1 to the position and divide it by 2, 1 plus 1 divided by 2 is 1. 3 plus 1 divided by 2 is 2. 5 plus 1 divided by 2 would be 3. So if I take the position and add 1 to it, divide it by 2, that will be the number of triangles. So if I ask you the 49th position has how many triangles? You would add 1 to 49 to get 50 and divide it by 2 to get 25. So 1 more than the position divided by 2 gives you the number of triangles if the position is odd. Alright, now we need to do the same thing with the parallelograms. Our generalization, if we look at the parallelograms, looking at the evens, 2 is 1, 4 is 2, 6 is 3, 8 is 4, 10 is 5. So again, we're using the counting numbers just like we did with the triangles. So now I can say if the position is even, I would take 1 more No, I don't take 1 more. I just divide it by 2. Because if I take 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3, 8 divided by 2 is 4, and 10 divided by 2 is 5. So if the position is even, you would take the number divided by 2 to get the number of parallelograms. But what if the position is odd? 1 to 0, 3 to 1, 5 to 2, 7 to 3, 9 to 4. So the difference is 1, we have 0, 1, 2, 3, 4, so this time if I add 1 and divide by 2, that's going to give me the number of triangles. So this time I'm going to need to subtract 1 and divide by 2. So if I have 1 minus 1, that's 0, over 2 is 0. 3 minus 1 is 2, over 2 is 1. 5 minus 1 is 4, over 2 is 2. So if the position is odd, then you would take n minus 1 divided by 2. And that would give you the number of parallelograms. So the generalization that we find for this particular problem isn't just one equation or one value for n. We look at the evens and odds separately for each of those, and that allows us to come up with our generalization. Now this would be for an upper middle. So we started out with an activity that would be very elementary, first grade, looking at patterns, what happens next. And now we are taking that same type of activity, still looking for patterns, but we are expanding it to where it would be more an upper middle or advanced lower middle class. All right, let's do another together, and then I will have your assignment for you. Let's start out with the hexagon as being first shape. Then we will have our hexagon with our parallelogram. Then we have our hexagon with their parallelogram with our square. I bet that is not a parallelogram. I bet they're using the rhombus. So let's go back and get the rhombus. And now the square should fit to be our third shape. All right, our fourth shape will be our hexagon, our rhombus, square, and a hexagon. Our fifth shape will be a hexagon, a rhombus, a square, a hexagon, and a rhombus. Scoot it over a little bit so you can see. And so now you should be able to see the pattern that's forming. And if I ask you what shape you would have for the sixth position, you should be able to see by looking at first, second, third, fourth, and now the fifth, and what would happen sixth. So if I ask you what shape would end the sixth position, you should be able to say what would end the sixth position would be the square. Now, as we continue trying to analyze what would happen on the 10th position, what shape would end the 10th position, what would the 10th position look like, how many hexagons, how many squares, how many rhombi would you have, we need to create our table with our position, the number of hexagons, the number of rhombi, the number of squares, the position, so we would count what we've created, and then from looking what we created, we should be able to see what would happen next without actually building what happens next. So we have one hexagon in the first, in the second we have one, in the third we have one, in the fourth we have two, in the fifth we have two. So based on that, what we have so far, it looks like the hexagons are going to increase every third or every fourth pattern. So they remain the same for 3. On the fourth, they would increase. So I am expecting that on the 6th position, there would only be 2 hexagons. All right, for the rhombi, there are none on the first. There is 1 on the second, 1 on the third, 1 on the fourth. On the fifth, there are 2. Now, based on this pattern, it looks like that on the 6th, there would still be only 2. because it looks like, again, that the rhombi are going to change on every fourth situation. There are no squares on the first, none on the second, one on the third, one on the fourth, one on the fifth, but on the sixth position, we're going to add a square. So there would be now 2 squares on the sixth position. So I see a pattern forming by looking at what we are able to count. And I know that there's going to be a change on every fourth number of the pattern. So we begin then seeing a pattern that is forming. So let's see if we can think about what would be happening on the 20th position. So how many times would the hexagons increase from 6 up to 20? So we need to count, look at a pattern. So how many groups of 3 are there between 6 and 20? Well, 7, 8, and 9, I'm predicting would have 3 hexagons. 10, 11, and 12, I'm predicting would have 4. 13, 14, and 15 would have 5. 16, 17, and 18 would have 6. So 19 and 20, I think, would have 7. So you can see how you can continue looking at the groups of 3 to see how many there would be of each in the 20th position. Alright, so now we're starting at 2, 3, and 4. Groups our rhombi. 5, 6, and 7 would have 2. 8, 9, and 10 would have 3. 11, 12, and 13 would have 4. 14, 15, and 16 would have 5. 17, 18, and 19 would have 6. So we would predict that the 20th would have 7. And then you could do the same with the squares. And so even no matter what I ask you, you would think of how many groups of 3 there would be from the pattern that you know to the pattern that you are looking for. Now, patterns can get more complicated depending on the age group that you are working with. You can begin looking at a hexagon, adding a triangle, and then letting that be the pattern. So this pattern repeats every third situation, like similar to what we did before. This pattern we know what the fourth position is and the third, and you want to work backwards to try to unravel to predict what would be the second and the first position. So what did I add to the third to get the fourth? That's what I'm going to take away to get the second. So if I added, let's say I have the difference between the third and the fourth is a triangle in front and a triangle behind. So the fourth looks like the third now if I take these two triangles away. So what has been added to this are the triangles on the end. So if I take those away, I get this. So what if I take away the two trapezoids and let this be the second? And then I take away the two triangles, and this would be the first. So the first is a trapezoid. I added two triangles. The third, I add two trapezoids. The fourth, I add two triangles. So what are we going to add on the fifth? Well, we would add two trapezoids. And then again, if we want to analyze, we set up our table. We count the number of triangles and the number of trapezoids in each, and then we look at them separately in an odd position compared to an even position, like we did on the very first examples.